Today we are going to learn about gradient descent variance, choosing the right optimizer. We'll explore various gradient descent algorithms, their strengths and weaknesses, and how to select the best one for your specific AI model application.
Welcome to our deep dive into the world of gradient descent variance. In this video, we'll explore the central role that gradient descent algorithms play in optimizing AI models. Understanding these optimizers is crucial as they directly influence the efficiency and effectiveness of your training process. By the end of this video, you'll have a solid grasp of the strengths and weaknesses of various gradient descent methods and be able to select the best one for your specific application needs. So, let's embark on this learning journey. Gradient descent is the foundation of many optimization techniques used in machine learning. At its core, it is an iterative optimization algorithm used to minimize a function by moving in the direction of the steepest descent. Mathematically, it involves calculating the derivative of the loss function, which indicates the slope of the function at a given point. By iteratively updating the parameters in the opposite direction of the gradient, we can find the local minimum of the function. This process is crucial in training machine learning models, as it helps in finding the optimal set of parameters that minimize the error. Implementing gradient descent involves initializing parameters, computing the gradient, updating parameters, and repeating the process until convergence.
Stochastic Gradient Descent, often abbreviated as SGD, is a variant of gradient descent that updates parameters using only a single sample or a small batch of data rather than the entire dataset. This stochastic approach introduces noise into the gradient calculation, which can potentially lead to faster convergence compared to the standard gradient descent. However, this noise can also cause the optimization process to become more unstable and may lead to fluctuations in the convergence path. Despite these challenges, SGD is widely used due to its computational efficiency, especially in scenarios involving large datasets. To mitigate the instability, techniques such as mini-batch gradient descent are often employed, striking a balance between the stochastic and deterministic approaches.
Momentum is a powerful enhancement to the basic stochastic gradient descent algorithm. It helps accelerate the convergence of SGD by adding a fraction of the previous update to the current update. The concept is akin to a ball rolling down a hill, which gains momentum and continues moving in the same direction even if the slope decreases. By incorporating momentum, the optimizer can navigate through shallow valleys and avoid oscillations. This results in a faster and more stable convergence process. Implementing momentum involves introducing a parameter, usually denoted by beta, that controls the contribution of the past update. This simple yet effective modification can significantly enhance the performance of SGD. AdaGrad, short for Adaptive Gradient Algorithm, is an optimizer that adapts the learning rate based on the parameter's frequency of updates. This adaptive learning rate is particularly beneficial when dealing with sparse data, as it allows for more fine-tuned adjustments. The core idea is to scale the learning rate inversely with the square root of the sum of all the historical squared gradients. This ensures that frequently updated parameters have smaller updates, whereas infrequent ones receive larger updates. However, a notable challenge with AdaGrad is the diminishing learning rate, which can eventually become too small and hinder further learning. Despite this, AdaGrad is particularly useful in scenarios where features are sparse and require careful handling.
RMSProp, or root mean square propagation, builds on the strengths of AdaGrad by introducing a decay factor to the learning rate adaptation process. This decay factor helps prevent the learning rate from diminishing too quickly, maintaining a stable learning process throughout the optimization. RMSProp is particularly effective in handling non-stationary objectives, which are common in dynamic machine learning environments. By maintaining a moving average of squared gradients, RMSProp adjusts the learning rate more effectively, ensuring convergence without the pitfalls faced by AdaGrad. This makes it a go-to optimizer in many practical applications where stability and adaptability are essential. The ADAM optimizer, short for Adaptive Moment Estimation, is a versatile and widely adopted optimization algorithm that combines the benefits of both momentum and adaptive learning rate methods. ADAM computes adaptive learning rates for each parameter by maintaining a running average of both the gradients and their second moments. This dual approach results in faster convergence and improved performance across various machine learning tasks. ADAM's adaptability makes it suitable for a wide range of applications, from computer vision to natural language processing. However, like all optimizers, hyperparameter tuning is crucial to maximize its effectiveness. By carefully adjusting parameters such as the learning rate and decay factors, ADAM can outperform many other optimizers. Choosing the right optimizer involves a comprehensive understanding of the strengths and weaknesses of each gradient descent variant. For instance, while SGD is computationally efficient, it may struggle with convergence stability. Momentum accelerates SGD, but its effectiveness can vary based on the problem at hand. AdaGrad is excellent for sparse data but suffers from diminishing learning rates, whereas RMSProp provides a more stable alternative. ADAM stands out due to its adaptability but requires careful hyperparameter tuning. A comparative analysis of these optimizers reveals that there is no one-size-fits-all solution. The choice depends on factors such as data characteristics, computational resources, and the specific requirements of the task. Understanding these nuances is critical for selecting the best optimizer for your AI project.
Despite their widespread use, gradient descent methods are not without challenges. One of the most common issues is convergence, where the optimizer struggles to reach the global minimum. This can be exacerbated by inappropriate learning rates, leading to overshooting or slow convergence. Overfitting and underfitting are also prevalent, often requiring careful regularization and dataset adjustments. Handling noisy gradients is another critical aspect, as it can lead to erratic training behavior. Effective troubleshooting involves a combination of strategies, such as learning rate annealing, gradient clipping, and data augmentation. By understanding and addressing these challenges, you can enhance the robustness and performance of your optimization process.
To bring the theoretical discussions to life, let's explore some real-world case studies where optimizer selection played a pivotal role in project success. In one scenario, a natural language processing task benefited significantly from Adam's adaptability, leading to faster convergence and improved accuracy. In another project, RMSProp was chosen for its stability in a computer vision application, where non-stationary objectives were a concern. These examples highlight the importance of carefully weighing the unique requirements and constraints of each project when selecting an optimizer. By learning from these case studies, you can gain valuable insights into the practical application of gradient descent variants in diverse AI domains. As we conclude this exploration of gradient descent variants, it's clear that selecting the right optimizer is a critical step in training effective AI models. Each optimizer offers unique advantages and challenges, and the best choice depends on the specific needs of your project. Experimentation and thorough understanding are key to making informed decisions. We encourage you to continue learning, experimenting, and applying these insights to your AI endeavors. Thank you for joining us on this educational journey, and we hope you've gained valuable knowledge to enhance your skills in AI model optimization.